You need to. All right. Welcome, everyone. Thank you for joining us. We're fortunate to be joined by Matthias Samland from MPIA. I'll always remember Matthias as the only person who I know who has combined transit and direct imaging methods together. He did his PhD also at MPIA and is there as a postdoc now and is going to be talking to us about characterizing exoplanets and disks from the ground in space. So thanks for joining and take it away, Matthias.
Yeah. Thank you very much. I'm Matthias Samland. I'm from MPIA in Heidelberg, as Kevin introduced. And I will give a relatively broad overview about what I've been doing over the last couple of years. So roughly speaking, I am interested in direct imaging. I do everything that you can see around a star. So planets, protoplanets, disks, CBDs. I do both astrophysical characterization of these objects, but also development of algorithms and pipelines. Yeah. So the first part of the talk, I will briefly introduce high-contrast imaging and what we understand as high. Yeah, come in.
But yeah, it's probably locked.
Okay.
And we just keep that open.
Okay, so the problem in high-contrast imaging is we have something that is very faint and you want to make it more visible. So we need to use all kinds of techniques to make this happen and to increase the contrast of our observation. And in reality, this looks something like this. We have an image of a star. This is taken with the sphere instrument. And you see that there's a lot of glare around the star. This is the speckle pattern that is introduced by, for example, having the atmosphere, perturbing the signal of the star, but also imperfections in the optics of the system. And the real problem is to try to find now something that is hidden in the glare of the star. So let's say there's a planet here. How do we make that here visible? And there are multiple ways of getting rid of the star. I would say the first way, or the best way, is to prevent the starlight from hitting the part of the detector where the planet is in the first place. And there are many ways of doing this. The easy solution is just build a bigger telescope. Because if you build a bigger telescope, the resolution of the telescope will increase and the point sources will be better resolved from each other. We can also use adaptive optics to basically put all of the starlight into almost spherical point and reduce this aberrations around the star. We can build a chronograph, so we try to block out the signal of the star while letting the light from objects that are next to the star still through the chronograph. So that's the tricky part, blocking the star but not blocking the planet together with the star. And the most extreme way is to build a star shade, which is basically a coronagraph, but it's flying outside of the telescope and preventing the starlight to enter the telescope in the first place. Then another obvious solution is you can observe the star at a wavelength where the star is faint and the planet is bright. So that's why most observations are done in the near-infrared or the mid-infrared for planets. And especially you target young objects so that they are still hot. And the contrast between the star and the planet is better. So this is a star shade, not to scale. So you try to block out the light of the star before it enters your telescope. And it looks very impressive. In the US here, they are trying some experiments to build these things. But I think the funding to actually launch one of these is not really there at the moment, which is a bit of a shame. Right. So what I was talking about now is basically prevention. Like, how do you engineer your way out of the problem? And I'm very happy that a lot of engineers are working on this problem and try to solve this for us. The other big aspect is diversity in the data. So the star and the planet, they are not the same thing. They have very different properties. So we can look at the data and on different observing strategies to try to disentangle those two signals in the post-processing of the data, or in the using special techniques that we specifically design instruments for. Okay, so this is what I will be focusing on now. And to give a short overview about what diversity is, as I mentioned, it's a difference between the star and the planet. And that comes in different flavors, or you could call it dimensions. We have, of course, the spatial dimension in which the signals can differ. We have a temporal dimension, we have a spectral dimension, we have polarimetry as well. There's other ways in which the star and the planet can be different, but these are, let's say, the major four. And the spatial is just what I talked about before, basically taking an image and trying to pull apart the two signals in the first place. The temporal diversity is quite interesting. For example, if you look at a star and you see a planet transiting the star and dipping the light, blocking light from the star, you see a change in the light curve signal. So you can still infer that the planet is there because of this introduced time-dependent signal from the planet, even though you're not really resolving the system spatially. Another way is, of course, spectra, because planets have very different spectra from stars. They are much cooler. You can do this at low resolution, you can do it in high resolution, and in both cases, these objects look very different. And in the case of polarimetry, usually starlight is considered to be mostly unpolarized. Whereas if light gets reflected off the surface, for example, a disk or a planet, it gets polarized, and you can filter out only the component that is polarized and thereby extracting the planet signal. Now, the fun starts that in reality, we don't just observe one of these things. Usually we observe a combination of these things. So for example, we combine the spatial information and the temporal information by something we call angular differential imaging. So we use the rotation of the sky. The star light itself is kind of fixed because the PSF, the point split function of the star, is only determined by the optics of the instrument. So that stays relatively the same, but the planet moves because the sky is rotated. And this movement of the signal of the planet with respect to the star can be used to extract the planet signal. On the other hand, you can also observe spectra in a temporal way and extract, for example, using high radial velocity measurements of the lines to extract the signal of the star because it's moving on a Keplerian orbit. Sorry, the signal of the planet because it's moving on a Keplerian orbit around the star. Lastly, I want to quickly talk about spatial and spectral here. So when you take, this is also an image from sphere here, it's going through different wavelengths. So if you observe an object at different wavelengths, the point spread function of the star will get larger as the resolution of the instrument decreases. So it seems to expand in size. But of course, if you have a planet at a certain separation from the star, it will stay fixed regardless of what wavelength you look at, because it's just at a specific point in the sky. Okay. So we use these differences in the data to model the data and to extract the signal of the planet. And that's two different ways basically to do this. One is to actually build a model of the instrument and model the data that way. This is usually very complicated for ground-based observations because you have the atmosphere perturbing things and you have a lot of optics. It's usually only used for space-based observatories like JWST. Like some of you might have worked with PSF, which is basically doing this. It's building a PSF of the instrument that you can then use to subtract the star. I will focus on data-driven models. Okay, so how do we do this? I told you about this nice situation where we have a planet signal that's moving. And by the way, this is not really a planet signal. This is just an artificial signal I put into the data because planets are so faint that you wouldn't be able to see them moving through the spectral halo. And as you can see, there's a bit of a problem because The easiest way to subtract the star signal here is to just subtract two images from each other, because the star is relatively unchanging. And if you subtract two images, it will get rid of the star. But because the planet is moving away, you will retain some planet signal. But because the sky is rotating at a certain angular velocity, if the signal of the planet is far away from the star, it will move relatively quickly over the detector. If it's very close to the star, it will move very slowly over the detector. So if you subtract images from each other and the planet is close to the star, you have to deal with that you subtract also out the planet signal, which is not what you want. You just want to get rid of the star. So during my PhD, I developed a method that is using transit light curves, or what I call transit light curves. It's a time domain approach to solve this issue, published in 2021. It's called TRAP, so that stands for Temporal Reference Analysis for Planets. And it's very good at trapping planets at small separation from the star. So how does this work? We see the planet moving here on the detector. That means it is touching, the planet signal is touching certain pixels on the detector. And if you select one of these pixels, you can look at the light curve or the time series of this pixel, and you get something like this. You see a lot of systematics in the data because the speckle pattern is changing a little bit, the stars flickering and so on, or jittering around. But if you look closely, you will see that there's a planet contribution hidden in the signal. If you don't know the systematics, though, you wouldn't immediately say maybe that there really is something there, because you do have a relatively strong impact from the star. So we have to get rid of these systematics, and the way that I do this is I take pixels, other pixels in the image, and I train a machine learning model on identifying the main temporal trends in the data. And then we want to fit this to the data. Let's take this pixel series here. We have our temporal trends. In this case, it's just simply a PCA decomposition of the other light curves in the image. And we have our model of the planet signal going over the pixel. We can predict this very well because we know how fast the sky is rotating. We know how fast the Earth is rotating. Exactly. So we can solve this linear system of equations and basically get the amplitude of the planet signal out of this simultaneous fit. We do this, if we do this, we can very nicely reconstruct the systematics, even though we are only training it on all of the other pixels. Okay, this is just for one pixel, but you can of course do this for all of the pixels where you suspect the planet to be, and combine all of this information, because for every pixel, the transit light curve of the planet will look a little bit different. And it contains a lot of information. Now, this is just for one position where the planet is assumed to be. You can do this for a grid of possible positions on the sky, and test all of these positions and make a detection map to see where the planet is. And this is an example for beta pick, where you really nicely get out the signal here, compared to an observation using this more traditional image-based approach. And the reason why it works so much better here is because the dataset has relatively short exposure times. So you can really, it's a temporal model, so you get all of the little wiggles and the time series out of this. Whereas in the more traditional approaches, you have to wait for your planet to move. So all of the image training data that you have is like shifted in time with respect to the data that you want to subtract from. So if we bin down this to like 1 minute exposures, we kind of get a very similar signal to noise to the other approach. So this shows that we really benefit from using all of these small time scale changes in the data. Okay, lastly, I wanted to point out that I have a framework for sphere data. So if any one of you is interested in looking at certain sphere data, it has a huge repository by now because it has been active like since 2015 now. So there's more than 4,000 observations there. And I built this tool called Spherical, where you type in the name of the star that you want to reduce. It can be a debris disk, it can be a planetary system, and it automatically downloads the data from the archive runs it through my new IFS pipeline that I published in 2022, and uses the trap algorithm to detect all the point sources that it can find and automatically extract spectra as well. So this is the link already. It should go public soon after the JWST deadline, when I have some time to clean up the last things. But if you're interested in already getting access to it, just drop me an email. Another last thing I want to point out is it has a list of all the observations that have been taken with Sphere that is also regularly updated. So if you just wanted to say, like, filter all the observations that have good seeing, long exposure times, and are for stars that are within 100 parsec, you can easily do this reduction automatically now. Okay. So the last method thing that I wanted to point out in this talk is that once we find an exoplanet, the problem is, well, once we find a candidate, the problem is identifying whether it's actually an exoplanet or not. And you can see here an example. We have one real exoplanet here, but a lot of point sources in the field of view. It can be like 50 point sources if it's a grounded field. And you want to see which of these objects are moving together with the star and are really like gravitationally bound to the sun. This can get really annoying if you have a large survey with a lot of these background objects. So I had a master student who completely automatized this problem. Like, if you have multiple epochs of observation of some stars, and you give it the positions and the epochs of the point sources detected, it makes a statistical evaluation of whether it's more likely to be co-moving with the star, or if it's statistically in agreement with a background population of stars in that position on the sky with that brightness of the candidate. So this is also on GitHub, and you can use it. Okay, so science results. I've got recently, I did a postdoc with Matthias Samland in Stockholm, and he really got me interested into this question of whether large stars can have large planets, or whether massive planets can even have planets at all. That might sound like a silly question, but for a long time, there was a debate about this, because a massive star, like a B star or an O star, it has such strong radiation that it photo-evaporates the disk really quickly. So is there enough time to form a planet in the disk? And also, it's very hard to observe these stars with radio velocity or transit methods, because radio velocity, you need a lot of lines. These stars don't have a lot of lines. You need, for transit, if you have a large star, the surface area of the star that's blocked by the planet is not very large. So everything is difficult. So until recently, nothing good has been known about this, until the BEAST survey came along, which is by Matthias Samland. And I don't know what happened to this figure, but you can see that they found a massive planet that's very far away from the star. It's like 500 EU, roughly away. And there's another planet. So now there are two massive planets that have been detected relatively far away. So I thought to do this for an even younger population, like SCO-SAN is here in this survey, I thought to do this for some beat star sample in Orion, where this kind of detection of the planet would be closer to the star, but still not so close that it would be really challenging in terms of high contrast. But it would be within the field of view of the integral field spectrograph, so it makes it easier to identify and follow up on the candidates that you find. And Orion is very convenient because all of these stars are super close together in like absolute terms. So you can like just star hop between the different beat stars and use them as reference for each other to subtract. So we did this very efficient survey of 41 targets, which has just been completed at the beginning of this year. And I had a bachelor student who did an amazing job looking through all of the data and running it through my tools and seeing what we find. And okay, I don't know what happened to this plot either. Yeah, we definitely found already one brown dwarf. There's a bunch of other candidates that we are still following up, and also one candidate planetary mass object. This is very unfortunately very small here, but you can see a point source next to the star. And the spectrum, which shows here the strong water absorption feature When we tested it earlier, it wasn't like this. Anyway, I hope the other plots work. Okay, so that's all that I wanted to say about the ground-based stuff that I've been doing. If you have any questions, let me know.
That's a question.
Yeah, sure.
So what is so you mentioned that there are 8 of the active candidates
Yes,
around that 41 target.
yes.
Is that more than what you expected in the beginning, or it's like
So based extrapolating from the BEAST survey, we were expecting to have at least 1 or 2 exoplanets. It's a bit more tricky about the brown dwarfs because in the BEAST survey they didn't really find that many brown dwarfs. So it's very low number statistics anyways. At the time when we did this analysis, also the statistical paper from the BEAST survey is not out yet. So it's a bit hard. I think it was just accepted, so I need to recompute what is the distribution that we would expect. Yeah. But yeah, it's hard to say. Probably some of them will be real, but I can't tell you. Okay, I will shift now to JWST and focus on one work that we just published this year, where we took non-chromatographic observation with ECAM in the MINDS survey. So the MINDS survey is a MIRI meta-infrared disk survey. So MIRI is an instrument of JWST. Now you might wonder, why are we taking ECAM data? It's a GTO program, and for some reason we could also observe with ECAM. So the only ECAM observation that we have is this. And the PDA-70 system is a very famous system that was discovered, and well, the disk and the planet was discovered in 2018. So it has a protoplanetary disk, and it has 2 protoplanets that are in the cavity of the disk. Now, I think everyone knows about the system. And another cool thing is that at least the planet PDA-70C has a circumplanetary disk that is detected in our model as well. Okay. So we have data in 2 filters, 1.8 micron, 4.8 micron. And we can use ADI with this data as well. The way that it works in space is that you shift the you rotate the telescope a little bit. Unfortunately, with JWST, that's just a maximum of 10 degrees. But we could only get 5 degrees in this case. So it's really like a little wiggle. But even with just this little rotation, because the telescope is so stable, just subtracting the 2 roll angles, you already nicely can retrieve that there is a disk and that there are the 2 planets. So this is really a proof of how stable the instrument is and how nice it is compared with dealing with the atmosphere of Earth. But we thought, of course, we can do better than this. This is just like a simple subtraction. So one thing that you need to do is, like, if you want to study the planets, you need to get rid of the disk. So we use the hydrodynamical model that's passed through and binned down to the resolution of the instrument. And that also works really nicely. So if we do this, even in this roll angle subtracted image, we can already nicely detect the planets and measure the flux to a much higher precision than was possible from the ground so far. Okay, but just subtracting 2 roll angles is not very sophisticated. So there are ways, I won't have time to really explain this in much detail, to also retain the flux of the disk much more. I told you there's a 5-degree rotation. So most of the disk flux you will just subtract out when you do the subtraction. So you can do this in an iterative way where you would like extract some signal after the shift, after the subtraction, and preserve that signal and then subtract it from your data, do the analysis again with less disk signal contaminating the data, and repeat the process until you've kind of shifted all of the detected signal into your detection queue. Anyway, we can talk about this more during the session. Okay, so this is how it looks like with this iterative and more like flux preserving approach. Here you see the the narrowband filter at 1.8 micron, 4.8 micron, the medium band filter. And you see very nicely also the disk structure that remains in the image. In this middle row, we subtract again the model of the disk. And you see that there's a clear, strong asymmetry in the disk, which is very consistent with what hydrodynamic simulations show, that the accretion streamer that is caused by the planet C would look like as an overdensity in a material. And yeah, if we then also subtract the flux of the planets, we are left with a lot of structure around the star here that we tentatively termed as being consistent with there potentially being another point source there. And this also lines up with a point source that was discovered with sphere that is at the same location in past data. We still need to work more on this, of course, to distinguish whether it's like some sort of disk feature or really a point source. So there's follow-up observation planned with gravity to do this. Okay, so the new picture that emerges here is that not only do we have these two planets, we now see the accretion streamer that is connecting the outer disk to the inner part. We also, based on the flux of B, measured that there's a clear increase in the emission at 4.8 micron, which points to there also being a circumplanetary disk around the B component, which wasn't really established before. And yeah, there might be even one more planet. Okay. Good. Then the last topic that I want to talk about is recent work that I've been doing on the disk with JWST. And in particular, very exciting detection of evaporating comets or asteroids in one such debris system, which is almost submitted, I promise, very, very soon. Next week, that is submitted. Still waiting for the pesky co-author replies. Okay, so why are debris disks interesting? I brought with me a gallery of many debris disks that have been taken with JWST. I love to show this picture because it's just so stunning. But you can clearly see what a debris disk can look like, because it's like a scaled down debris disk. Debris disk means that you have some ongoing process that replenishes the dust in the disk that makes it visible. Like if you didn't have collisions in the rings of Saturn, if you didn't have ejection from the moons and so on, these disks would disappear. The same is true with debris disks. So debris disks are really the signpost of there having been successful formation of larger rocky bodies in the system, because you need some sort of collision and cascade that keeps them alive, that keeps the dust in the system, because it gets blown out otherwise by the radiation pressure, or it drifts into the star. We can learn a lot about them, like about the system architecture. In the solar system, we have the asteroid belt, we have the Kuiper belt, we have also the Venus, basically. We can learn about the dust composition. We can learn about potential active collisions still going on in these systems of larger bodies as well. Okay, a quick, nice gallery of the Venus here. You're probably familiar with, or maybe more familiar with protoplanetary disks and how they come in all kinds of different shapes. The same is true for debris disks. They can have rings, they can have eccentric rings, they can have gaps, arcs, walls, asymmetries, even spirals have been seen on these disks. So they are a very diverse bunch, and every debris disk kind of has to be treated as its own beast. I also wanted to get rid of a common misunderstanding about the debris disks. So a protoplanetary disk does not immediately translate into a debris disk. As I say, the protoplanetary disk disperses, and then you have collisions that make a secondary disk around the star. So it's not like you have just leftover dust that is lingering in these places. Okay. Right. So this is the dust, but recently a lot more attention has been paid also to the gas and debris. And one way, and this has already been done for Beta Pictoris in the 80s and early 90s, with high resolution spectroscopy, you can see absorption lines that are time variable. For example, in iron 2, there is evidence for them to be exocomets that go in front of the star, and the coma of the comet absorbs light from the star in these wavelengths. So recently there was a very nice paper by Renaud that looked at all of the data that has been taken for beta pig. So that's one way. There was actually evidence for there to be some planets around other stars before there have been exoplanet detections. Okay, but in terms of emission, it was only also done in the last 10 years because this gas in emission is relatively cold. It's a couple of Kelvin, tens of Kelvin. And you need really sensitive instruments like Herschel and ALMA to even detect the gas. So with ALMA, I think the only gas species that has been found is CO. There have been searches for other gas species, but they haven't been found. And with Herschel, you see stuff like oxygen and carbon. And also for these disks, there's the question: is it primordial? Is it second generation gas? I think more or less the consensus nowadays is that it's also second generation. Okay, and the thing is that no gas emission lines in the mid-infrared have been found before JWST. So in the MINDS consortium, we not just observed these wide range of masses of protoplanetary disks, but we also included 5 CO-rich debris disks, and 4 of them are more cold and extended disks, and 1 of them is a warm disk. And we observed it with MIRI MRS. So this is a coverage from 5 to 28 micron, roughly, at a resolution of 3000, which is very good. And we took this data to search for gas emission lines. And these are the 4 cold and extended disks that we see. And you see a lot of wiggles going on, but unfortunately, we couldn't identify a single line in this spectrum. There's like photospheric absorption lines from the star, but at longer wavelengths, everything that you see is basically residual noise or artifacts in data collection. So that was very disappointing. But I told you we have 5 disks, so not 4 disks. So the exciting outlier here is the one that has an asteroid belt analog disk. It's very compact, like the disk only extends, the warm part of the disk only extends about 10 AU. And it is actually a stellar twin of Beta Pictoris. So it's the same spectral type, it's part of the same moving group, it's also the same age. And it has roughly the same spectral type. Oh, it's already saying it has the same spectral type. And it has a very strong silicon feature, which is what you get when you have warm, small dust grains. So this was already seen with Spitzer in 2009 and 2012, where they analyzed the composition of the dust in the system based on the silicon feature. And the conclusion there was that you need some high velocity collisions to make this kind of mineral composition. It was also imaged with SPHERE, with the simple instrument in polarimetry. And you see that the system is relatively nicely edge-on. It has an inclination of 75 degrees roughly. And it really doesn't extend very far, at least in these small scattered light dust grains. There's also the CO detection. Unfortunately, the resolution of the data that is currently published isn't very good. You just see that there's CO up to like 10 AU or so in this data. Okay. So what does the JWST data look like? The JWST data looks like this. So in black, you see the spectrum we have obtained with the MRS instrument. The pink line shows the past Spitzer observation. And you can see that they are very similar. So this the system seems to be very stable in terms of the dust properties of the debris disk. The difference here is maybe 5%. So it's kind of within the margin of error of the calibration. Might be a real change, but it's not a super significant change. So in Beta Pig, for example, there was recently a paper where they found that the silicate features changed wildly over the last 20 years. So these observations are 20 years apart, roughly. And they take that for being like just one giant collision that makes a lot of dust, and then the dust disperses and the silicon feature changes. This is probably not the case for this system. But if you look very carefully, you might notice that we finally see some lines. And they are very exciting lines. They're also very excited lines. Let's say not so surprising ones are nickel and iron, because that's what you get from comets and asteroids very easily. But we also see a very strong chlorine and sulfur feature of neutral chlorine and neutral sulfur. And this was great when we saw this. So it's basically all the stuff you imagine as space rock. You evaporate a space rock, and this is what comes out of the space rock. We don't see any molecular lines. There's no hydrogen, no CO, no H2O, no methane, no CO2. There's nothing. So these atomic lines is everything. Which points to the suggestion that it's really secondary disk and not a primordial disk, because if it were primordial, we should have probably seen the H2. Okay. We don't detect argon-2 either. So argon-2 has been detected in Beta Pictoris. And it's it's a noble gas. It's very volatile, right? So it needs to be somehow trapped and released. Because otherwise, if it's not trapped in a stable, in a solid body, it would be get rid of the system over these timescales. So this points to the fact that maybe we don't have so many icy bodies in the system that we're observing. So this asteroid belt is more like a dry asteroid. Okay, where do these lines come from? And we really struggled to answer this in the beginning. It could come from the main asteroid belt. It could be the recent giant collision that releases this belt. Or it could be these evaporating objects close to the star that we also know from UV and optical spectroscopy that they are in the system. Okay. And fortunately, the spectral resolution of MRS comes to the rescue, because we could actually resolve the lines. All of the lines are spectrally resolved. So this is the chlorine line at 11 micron, and the gray lines show the spectral resolution of the instrument. So you clearly see that it has some velocity component there. And the same we see really for the other lines as well. As you go to very long wavelengths, the resolution, of course, gets worse of the instrument. So you stop seeing it really resolved, but you can clearly still see it's broadened, and maybe it's even a little bit asymmetric. Okay, so what I did is I make a simple gas model of a rotating Keplerian disk, and see what velocity profile fits these lines. And this works quite well, and you can sort of constrain from what separation from the star does the emission come from. And the picture that emerges here is that we have this emission that we've seen with the other observatories that's more coming from, let's say, 4 AU to 10 AU, around this range. But the new gas that we detected is really, really close to the star. So this iron, nickel, and chlorine is probably within 0.3 AU from the star. And the sulfur seems to be a little bit further away from the star, at around 0.5. Okay, so what explains this? We think this really points to asteroids from the asteroid belt being perturbed and approaching the star. Because at these separations, if you just compute the black body kind of equilibrium temperature, you're already above 700 Kelvin. And here you are at 1,200 Kelvin. So if you get a Stargazer comet, it will really start evaporating and falling apart, releasing stuff that's inside. So this also kind of points to there being maybe a planet or something that perturbs the disk. And yeah, it will be exciting to try to look if we can actually detect the planet in the system. Okay. So I think we can answer this now. It's most probably, really a rain of these objects that get broken apart by the temperature of the sun. Okay. This also really opens the window to trying to start understanding what these asteroids might be made of, because we can compare them to objects in the solar system. Right? So we know that iron and nickel is released in comets, for example. And we also know that iron and nickel is an iron and nickel meteorites, right? Okay. We can also compare the line intensities with different objects. So in beta pig, we have these lines, and for iron and for HD 17255. And it seems like the emission from HD 17255 is much hotter than in the beta pig system. And this also agrees with the broadening of the lines, because in the MIRI state of beta pig, the line broadening is much smaller than what we observe. So we can try to understand the physical conditions of the gas. Okay. We can also think about where does the chlorine and the sulfur come from, because we also have measurements of asteroids and comets in the solar system, where they basically have these sample return missions or in situ observations. And for example, chlorine tends to be in these kind of ammonia salts. And you could try to correlate this with the temperatures at when these kind of materials get released, and see if we can detect some sort of composition gradient, for example. You would, as we see, like sulfur, for example, seems to evaporate earlier and further out, which kind of makes sense. Whereas metals are much harder to release in general. Okay. We can also try and start to connect this with the whole sequence of when do these materials form and get incorporated into dust and ices and systems, from protoplanetary disk to now the finally formed product of the planetary systems. Also very exciting and very timely, because there's just this comet that can be seen in the sky. We have star grazers, or sun grazers in this case, in the solar system that we can study and see how they fall apart as they get close to the star. So the most famous of these is 3200 Phaeton, that has a period that brings it regularly very close to the star. It heats up to like 800 Kelvin, releases a bunch of stuff, and goes again on the orbit. So studying this kind of objects and comparing it to what we see in this kind of debris disk is very interesting. That brings me to the conclusion of this part, and also the last part of my talk. So it's very exciting that we see the slides and debris disk. We can finally start doing asteroid composition studies in other systems, and maybe link it to planet formation and other processes to see how everything connects together. And yes, the sphere is old, but it's still interesting. So feel free to talk with me about all of the data reduction tools if you want to use sphere in the future or based on archival data. Yeah, thank you very much.
Very nice talk about it. I had a question about the trap method, and so I was curious how you pick the area around the planet, and if it's dependent on like the PSF sampling of the planets and things like that.
Yes.
By the data stuff.
Yeah. So that's exactly right. We use a PSF model from the start. Usually it's just an unsaturated image of the star. And we use that to construct this light curve model. So basically, I just take an empty data cube, I inject the planet in all of the frames, and then I select the pixels based on that. And so if you change the position of the planet on the sky with the field rotation, basically, you can create this trajectory on the detector and select the pixels based on that. And then I exclude that area that's affected by the planet from the training data that I use to make the systematics model. And I have tested it. I use it also on the NIRCam data for PD70. But as it is implemented right now, TRAP is optimized for finding point sources. So it got the disk and the two blobs, but it's not really. It doesn't deal super well if you have point sources and a lot of extended structure around, because the forward model just doesn't take it down. Like you could make a model with a disk as well. You could, like, instead of doing this kind of a grid-based trajectory model, you could inject a model with an MCMC of a disk, for example, and still do the kind of light curve analysis, but that's not really implemented.
So I have a question regarding the last part.
Okay.
Are you able to get the rough estimate of how much elements you have or how much of the gas is in there as you compare that to asteroids coming to observe our system?
Yeah, that's the goal, I'd say. This first discovery paper focuses on just, hey, we found these lines. Let's interpret them, model them, and think about what it all means. It's not as easy. You could probably do a very simple toy model, and it would be terribly uninformative. Because we only see one line. Like we see one line of chlorine, we see one line of sulfur. And without putting a lot of additional modeling into it, like the UV flex from the star, etc., it's a bit tricky to really answer this immediately. I'm sure it can be done with some more work.
Yeah, so kind of related to that, do you expect these features to be short-lived or long-lived? So like, would it be beneficial to do like a time domain type of study for this?
Yeah, I'm writing a JWST proposal to monitor the system at least. I think it will probably be relatively stable because we see how stable the rest of the system is, or how unstable the rest of the system is, I guess, because the dust features haven't changed for 14 years, basically. And also, you can see a relatively constant, well, no one really has done that analysis, I think, but in early data, checking the exocomet activity with UV and optical spectroscopy, you see these features, and in new data, you also see these features. So I think it's an ongoing process, but of course, we really have to take the data and look and see if it changes. Yeah. Unfortunately, Spitzer has not high enough resolution and sensitivity to see these lines.
I guess actually go ahead.
I have a question about the trap algorithm also. When you block out where you think the planet might be, and then use the rest of the pixels to model the noise, is that just modeled across the entire image, or do you do that with radius?
Yeah, it's this geometry. So in this case, the planet is going here. So it's kind of like a heuristically motivated approach, because you think that the speckle like statistics are pretty similar and the same separation from the star. But there's also, when you think about optics, Fourier optics as well, a good argument to make that a lot of features have point symmetry in the image. So I include all of these pixels on the other side of the star as well. But then you also have things like the spiders, which are extending in the same direction of the star, like azimuthal direction of the planet, sorry. So I also include like a bunch of pixels inside and outside of the planet to try and capture them. And it seems to work okay. There's probably, I don't know, a bachelor, master thesis work on optimization that can be done there. Like correlation analysis and whatnot, but this seems to work.
I guess I was curious about the status of the MIRI wavelength solution. I know it's been updated a few times. I was curious if your collaboration does their own custom approach.
No, we don't. Yeah. I think with the last update, it's pretty good. It's like below 10 kilometers per second for the absolute calibration. But I mean, if you go like measure the width, for example, that should be better than the absolute.
Any questions from online audience?
So all of your cold disks don't show this nice silicon picture. So can we assume that there's very little dust reduction?
Well, I wouldn't say no. Like some of them really don't have any silicon feature. Some of them have a little bit of a wiggle. Like you can see here, for example,
Yeah, right.
there's like a little bit of something. This one doesn't seem to have anything. Here, there might be a bit of silicon mesh. So yeah, you would think that maybe, oh, this one has a silicon feature, so it should have lines, but it doesn't seem to be a 100% correlation. And then none of these disks we see Argon, for example.
Curious for the list that you detected the new lines. You mentioned that in the speeder data we don't have the quality. Can you see anything? But do we see any like of this kind of hint in the speeder data?
That's really there's okay. Let me just if you really know that there might be something there. For the sulfur line, you might see. If you don't have any information, I probably won't believe that. So yeah, it's tricky. It's very tricky because just you see so much larger and the resolution is low. For nickel, iron, chloride, no chance.
Maybe there's another question that's but you don't get.
Very much.